Quantum error correction is a crucial aspect of quantum computing that addresses the inherent susceptibility of quantum systems to errors caused by various factors, such as noise and interference from the environment. Unlike classical bits, which are either in a state of 0 or 1, quantum bits or qubits exist in a superposition of states, making them more vulnerable to errors. Quantum error correction aims to mitigate these errors and preserve the integrity of quantum information. Key principles and components of quantum error correction include quantum superposition and entanglement. In a quantum computer, qubits can exist in superpositions of 0 and 1 simultaneously, and they can be entangled with each other. These quantum properties are fundamental for quantum computing but also make qubits more susceptible to errors. Quantum gates and operations. Quantum gates are the building blocks of quantum circuits and operations. Errors can occur during the application of quantum gates due to factors like imperfections in hardware, environmental noise, and decoherence. Decoherence and noise. Decoherence refers to the loss of quantum coherence over time, leading to errors in quantum computations. Noise from the environment, temperature fluctuations, and other external factors can introduce errors and disrupt quantum states. Quantum error correction codes. Quantum error correction involves the use of specialized codes, known as quantum error correction codes or quantum codes, to detect and correct errors in quantum states. These codes are designed to encode qubits in a way that makes errors detectable and correctable. Qubit redundancy. Quantum error correction often employs the concept of redundancy. Information is redundantly stored across multiple qubits, allowing errors in individual qubits to be detected and corrected through the collective information of the redundant qubits. Syndrome measurement. To identify errors, quantum error correction schemes use a process called syndrome measurement. This involves performing measurements on ancillary qubits associated with each logical qubit to determine the presence and type of errors. Stabilizer codes. Stabilizer codes are a class of quantum error correction codes that use a set of stabilizer operators to detect and correct errors. Examples include the Shor code and the Stein code. Fault-tolerant quantum computing. The ultimate goal of quantum error correction is to enable fault-tolerant quantum computing. In a fault-tolerant quantum computer, errors can be actively corrected during computation, allowing for the construction of large-scale, reliable quantum circuits. Threshold theorems. Quantum error correction is theoretically grounded in threshold theorems, which provide conditions under which fault-tolerant quantum computing becomes achievable. These theorems specify the error rates at which quantum error correction can overcome noise and errors to achieve reliable computation. Experimentation and implementation. Researchers are actively experimenting with various quantum error correction codes and techniques using physical qubits in quantum computers. Implementing effective error correction is a critical step toward building practical and scalable quantum computers. Quantum error correction is a complex and rapidly evolving field, and its development is essential for the realization of practical and reliable quantum computers. As quantum hardware advances, researchers continue to explore new approaches to enhance the efficiency and effectiveness of quantum error correction techniques.